5.9 will be dealing with hyperbolic trig functions. And I'm not going to go into tons of detail about what hyperbolic trig functions are, but I just want to make a couple of comments in case you didn't watch the video from section 5.9 like you're supposed to. But um, the trig functions we're used to dealing with are what are referred to as circular trig functions. Um, we derive them off of right triangles to begin with, but then so that we can use angles that are greater than 90 degrees, then we base them on positions on the unit circle. So if we want to find sine of a given angle, it's tied to the y coordinate on a unit circle, or if it's not a unit circle, if that's r, that's y, and that's x, then the sine of our angle is y over r. Cosine of our angle is x over r. And then tangent is y over x. Hyperbolic trig functions are based on a hyperbola. Instead of a unit circle, which is x squared plus y squared equals 1, it's on a hyperbola x squared minus y squared equals 1. And remember, hyperbolas are things that go like that or go like that. So that's their definitions are similar, but they're also a little bit different. There are applications of them, so we'll go through the derivatives, but mainly what you need to be able to do is evaluate the functions and know how to do the derivatives and integrals. If you look in your book, I'll pull it up. Let me copy this over. These are the definitions of the hyperbolic trig functions. If we're trying to calculate hyperbolic sine, we calculate it by doing e to the x minus e to the negative x over 2. If we're calculating hyperbolic cosine, it's e to the x plus e to the negative x over 2. Tangent is still sine over cosine, so hyperbolic sine over hyperbolic cosine. Cosecant is still the reciprocal of sine, so if we know sine, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. So on this first problem, they want us to calculate this. So we will do e to the, our x is 1, and is it plus or minus? For sine, it's minus in between, so minus e to the negative x, which is 1, over 2. And then we can get that as a decimal approximation if we need to. So e to the 1 minus parentheses e to the negative 1. So that's the numerator divided by 2. So then we can just take that to however many decimal places we're asked for. 1.175. So that's just plugging a specific number into definitions for hyperbolic trig functions. If it were asked for cosine of a particular value, we would use this formula and we would plug our number in. So then they ask us to find a derivative. So let me pull up a list of the hyperbolic derivatives. So on the next sheet over here, we have a list of hyperbolic derivatives. They're very similar to the basic trig functions. Remember, the derivative of sine is cosine. Well, the derivative of hyperbolic sine is hyperbolic cosine. The derivative of cosine is negative sine, but for the hyperbolics, it's just positive. The derivative of hyperbolic cosine is hyperbolic sine. The derivative of tangent is still secant squared. The derivative of cotangent is still negative cosecant squared. For regular secant, the derivative is secant tangent. Here we get a negative. The derivative of cosecant is still negative cosecant cotangent. So very similar derivatives. And then the integrals are just going back the other direction. So if we want to find the derivative of this one, the derivative of hyperbolic sine is hyperbolic cosine. It's more than just x, so times the derivative of the inside. So we can call that 5 hyperbolic cosine 5x. Often we'll call, instead of hyperbolic cosine, we'll call it cosh, or if it's hyperbolic sine, we'll call it sinh. But technically it's hyperbolic. On this one, they ask us to find extreme values. So we need to take the derivative. So notice we have a product here and we have a product there. So we're going to have to do the product rule for the first term. So f prime is, if we call this u and this v, it's the derivative of the first term. So u prime cosine x times v plus u times v prime, and the derivative of sinh is cosh, minus parentheses the derivative of this. So the derivative of this one, for that one, that's u and that's v. So the derivative of cosine is negative sine times v plus u v prime. The derivative of v, derivative of hyperbolic cosine is hyperbolic sine. So if we distribute our negative, notice it's minus whatever that derivative is, and that derivative has two terms. So each of those get that negative. So we're going to have a cosine x times sinh. We're going to have a sine times cosh. Minus a negative will make that a plus sine times cosh. And minus a positive will make that minus cosine times sinh. So this one and the last one are opposites. Those cancel. The two middle ones are the same, so they just add together. So our derivative is 2 times sine times hyperbolic cosine. We want to find the critical points so that we can get the extrema, set that equal to 0. This is nice because we have a product, so we find out what makes each of those factors 0. So the first number, obviously, that can't be 0, so we're going to see what makes sine equal to 0 and what makes hyperbolic cosine equal to 0. So for sine, I suppose, I didn't copy this part down, they're going to ask us to go from 0 to 2 pi. So sine is 0 here and here. Remember, on the unit circle, sine is the y-coordinate. So y is 0 here and here. So when x is 0 and when x is pi. Now you might say, well, how do I do this one over here? Well, we're just going to convert this into e to the x plus e to the negative x over 2. Set that equal to 0. This is the definition for hyperbolic cosine. Multiply both sides by 2. So those are gone. So e to the x plus e to the negative x equals 0. We have a negative exponent, so we can take that to the denominator and call that 1 over e to the x. To make the fraction go away, multiply both sides by e to the x. So e to the x times e to the x, multiply like bases, we add the exponents. So get e to the 2x. When we multiply it times that one, e to the x and e to the x cancel. On the right side, of course, we just get 0. Subtract 1 from both sides. So we get e to the 2x equals negative 1. To get, since our variable is in the exponent, remember we can take natural log of each side. Natural log of e to a power cancels, so we get 2x equals natural log of negative 1. But remember, we can't take log of negative numbers. So since we can't take log of negative numbers, for that equation we tried to solve, there's not a solution. Which means when we set hyperbolic cosine equal to 0, there are no critical points there. So our only critical points are at 0 and pi. Now, to find out which one's a maximum and which one's a minimum, we could come back here and we can get the second derivative and use the second derivative test to find out at 0, are we concave up or are we concave down? And at pi, are we concave up or concave down, to determine if we have minimums or maximums. Or we could just test the slope on each side. We can make a number line and say here's 0, here's pi. Are we going up or down here? Are we going up or down here? Up or down here? Remember, at a critical up and then down, it's a maximum. At a critical point, if we're going down then up, it's a minimum. So I'm going to leave that part for you, but the main thing I wanted to do is to help you get the critical points here. So the next problem that we have actually involves doing an integral. We did a derivative with hyperbolic trig functions. Now let's do an integral. And if we look through our table, there's not per se an integral that deals with hyperbolic tangent. I don't think. I'll go back and check real quickly. So no, when I look back at my list, this is not necessarily one of those. But remember, tangent can be rewritten as sine over cosine. So this will be hyperbolic sine over hyperbolic cosine. We've done something similar to this back in chapter 5. If we let the denominator be u, the derivative of hyperbolic cosine is hyperbolic sine. So this part is du, this part is u. Remember, when we integrate du over u, that integrates into natural log absolute value of u plus c. But since this is a definite integral, we don't have to have the plus c. So natural log absolute value of u, which is hyperbolic cosine x. We want to evaluate that from 0 to natural log of 5. So we're going to plug in a natural log of 5. So we have natural log of absolute value cosh of natural log 5 minus natural log absolute value of cosh 0. So the antiderivative sinh over cosh, natural log, and then we plug natural log into there, plug 0 into there. So a couple of things here. We have a natural log minus a natural log, so we could write this as a quotient. We could write it as natural log of this one divided by that one. Or we could just simply evaluate this one, evaluate that one, and take the difference. Don't have a real feel for which one would be better. Let's just combine those natural logs and call that natural log absolute value of cosh natural log 5 over cosh of 0. So let's calculate that inside part. Cosh of natural log 5. So remember, cosh x is e to the x plus e to the negative x over 2. So if we put a natural log of 5 in, we're going to get e to the natural log of 5 plus e to the negative natural log 5 over 2. So here, e to a natural log power, those cancel each other out and give us 5. But that only works if our coefficient of natural log is 1, positive 1. If we have a negative 1 there, we have to move it up here. Remember, if we have an exponent inside a log, we can put it out front, or if we have it out front, we can put it up as the exponent. So e and natural log cancel, and that gives us 5 to the negative 1, which is 1/5, and that's over 2. So I'm just going to leave it like that for now. That's hyperbolic cosine of natural log 5. And then we need hyperbolic cosine, what was it, 0? Yeah. So we're going to plug a 0 in. So that's going to give us e to the 0 plus e to the negative 0 over 2. E to the 0 is 1. E to the negative 0, well, negative 0 is just 0, so e to the 0 is 1. 1 plus 1 is 2, so that makes 1. So on the inside of our natural log, we're going to have this one divided by this one. Remember, it was on the inside cosh of natural log 5 over cosh of 0. So on the inside, that simplifies to this divided by that. Well, anything divided by 1 is itself. So natural log of 5 plus 1/5 over 2. And then we just need to simplify that. Several ways we could get that as a single fraction and divide by 2. Or another technique to clear complex fractions is whatever denominator we're trying to get rid of, multiply top and bottom by that. So on top, if we multiply the top by 5, 5 times 5 is 25. 5 times 1/5, the 5's cancel. On bottom, 5 times 2 is 10. So that gives us 26 over 10, which that reduces. That's a positive number, so we don't have to keep it in the absolute value. So 13 over 5. So several things going on there. First off, home page. How do we integrate tangent? It's natural log of u. And then how do we evaluate natural log of hyperbolic cosines? That goes back to the first problem we did. We just need to know what is the formula for hyperbolic cosine, plug those values in, and simplify them. As we go on to the next problem, now we're taking the derivative of inverse hyperbolics. So we started out taking the derivatives of trig functions at one point, then we took the derivative of inverse trig functions. Now we've taken the derivative of hyperbolic functions, now we're taking the derivative of inverse hyperbolic functions. And as with any derivative, you just need to know what the formula is to get that derivative. So here are the formulas for the hyperbolic inverse derivatives. So we're doing the derivative of inverse cosh of u. So that derivative is u prime over the square root of u squared minus 1. So let's write that out. The derivative of inverse hyperbolic cosine of u is u prime over square root of u squared minus 1. And you probably noticed I went back to the formula sheet. These are not ones that I regularly commit to memory. There's your basic trig functions you want to keep in your memory, your exponentials, your logarithms and things, but a lot of your inverse trig, hyperbolic trig, these are ones that we may not always have memorized. So keep in mind, this is the derivative of 3x u prime over the square root of u squared, so 3x squared minus 1. So on bottom, we square 3x, so 3 squared and x squared minus 1. So that's our derivative. That's the derivative of inverse hyperbolic cosine of 3x. Then they ask us to do an integral, and there are easier ones, but I picked one of the harder ones. I figured if I can show you how to do one of the harder ones, maybe when you have one of the easier ones, it won't be so bad. But we look at the list of integrals. Similar to the regular inverse trig functions, we have some u squareds and a squareds under the square root, and we have a squareds and u squareds under the square root subtracted. So some of them have the u squared first, some of them have the u squared last. Now, if it's a plus in the middle, it doesn't matter what the order is, if it's u and then a or a and then u. But if there's a minus in the middle, this particular one has the u squared first. This one has the a squared first. So notice the difference between these two. And as I'm saying, notice the difference. I'm just reminded, I'm not sure that y'all are able to see the screen. I hope y'all are. Let me copy these just in case. So this is what I was saying about the a squareds and the u squareds. If there's a plus in the middle, this square root and that square root are the same. But if it's a minus in the middle, this has the variable part first, this has the constant part first. And then, of course, the obvious difference between these two is this one has a u in front of the radical, where this one doesn't. So notice this has something in front of the radical, so it makes us think it may be more like this one. So we're going to have to complete the square on this to try to make it a variable part squared and a constant part squared. So if we group the x squared and the 2x together, and then put the 17 over here, half of 2 is 1, 1 squared is 1. If we add 1, we also have to subtract 1 to keep it equal. So underneath that radical, we have, this is x plus 1 times x plus 1, so x plus 1 squared plus 16. So that's what's underneath our radical. So this is u squared. So u is x plus 1, which would make du 1 dx. This is a squared, which would make a 4. So it looks like we have du there, u here, and then the square root of u squared plus a squared, which is this one, using the plus sign. So when we integrate that, we get this using the plus in the middle. So that gives us negative 1 over a, and we'll come back and fill in natural log of fraction, where we have a plus, if that's a plus there, then we have a squared plus u squared, and then on bottom we have absolute fraction. All that plus c. So in our case, negative 1 over 4 natural log 4 plus the square root of this. So we could call that whatever, x plus 1 squared plus 16, or we could put it in the other order, over the absolute value of u. So absolute value x plus 1 plus c. And there's no need to simplify any of that. We can leave it like it is.